Hello, my name is Randy Boone, and in this video I'll be introducing the G-Range model. G-Range was the first model in the L-Range modeling family. It's what started us looking at the world in this way, and so I'll introduce the tool. I'll talk about where it came from, its origins, give a brief introduction into the way that vegetation is represented in the model. I'll talk of assessment, again briefly, the inputs and outputs from the model, how you can acquire the tool, and where it will live long term. Information will be stored and such. All of this will be done briefly, knowing that there'll be videos that follow that will be much more detailed. And we'll go into the specifics of how to use G-Range, the L-Range model, and other tools that we're distributing. When I first came to Colorado State University 25 years ago, I began by using a model called Savannah, the Savannah Modeling System, written by Dr. Michael Kogenaar, a very comprehensive and powerful model representing, if you wish, changes in individual vegetation species, for example. And so it, again, very powerful. By that I mean that once you had taken the time to apply Savannah to an area, the number of switches and levers in the model allowed you to address a diversity of questions. And so any scenario that might come up seemingly was appropriate for the Savannah model to address. Ultimately, though, after using it for many years, I decided that the complexity was a little overwhelming, a little bit too intense to apply, and really what I was interested in most often was providing forage for wildlife and livestock. And so, along with some colleagues, I sought an alternative. Part of that process then was developing a new model, as it turned out, G-Range, and I knew that I didn't want to start from square one. I wanted to build off existing models. So I did an exploration of models. Some were indeed too complex. Some were too simple. So, for example, you might have a quantity of grass, it's multiplied by some value to represent a growing season, and you end up with more grass. And it can represent dynamics well, but it's not happening through a process. And so the dynamics in an average year, say, may be represented well, but if there are changes in rainfall patterns or perhaps a drought or the like, it won't necessarily represent the changes that are associated with those rainfall patterns, say. Instead, I wanted a process-based approach where, for example, vegetation included was competing for nutrients, for light, for space, for water. And so similar patterns of growth may be represented, but it's happening through the processes involved. Some models were challenging to use. Now, they're used all the time, including here in the Natural Resource Ecology Lab. I'm thinking of Century and Descent, but they are point-based models. They're very well known, used around the world, but they are, as I say, point-based models. They represent a point in space. Now, they're typically applied to represent a homogeneous area or a given plot of crops or what have you, but what that means in practice is if you're interested in representing a county, say, you claim that county to be homogeneous, you run a Century application, say, for that county. But then if you want to represent the 3,000 counties in the United States, you'd run 3,000 simulations and summarize the results. And again, people do that all the time here. It works well, but it was just a little more complex than I wanted to pursue here. I wanted all of the simulation, so to speak, to happen in one process. And so that was a goal as well. Of course, other models that I reviewed were abandoned where they hadn't been cited in some time, or the code wasn't available, or the manuals weren't available, and so not useful to leverage. Ultimately, knowing that I wanted a biogeochemical model to be at the center of G-Range and the skills and experience that are developed here, I came to use the Century model as the foundation for the biogeochemical processes in G-Range. So one day formally went to the authors of Century and asked if I could incorporate the core of Century into G-Range, and did so. We created G-Range then to represent global rangelands. That's the G, global rangelands. And so you see the title of the talk here, the L-Range modeling family. That's the local modeling representation. The G-Range is for global questions. It responds to main climate variables. This is very common these days, where models are driven by, in this case, monthly rainfall and temperatures, minimum and maximum temperatures. Can represent the main biomass groups. This is the main trade-off between the quite complex models that I've spoken of and G-Range. And it is indeed a trade-off. There are pluses and minuses associated with this trade-off. But in G-Range, we're representing at the coarses level, and there's a little more detail than this would suggest, but at the coarses level, we're representing herbs, shrubs, and trees. Management practices are in place, including fertilization, grazing intensities represented, fire is included. I'm the primary author. Doctors Conant, Searsley, and Staubach were involved in developing the model as well. And the push to create G-Range and funding that enabled it to happen was provided by Dr. Philip Thornton and Dr. Mario Herrero, at the time with the International Livestock Research Institute, and later on Mario was with CSIRO in Australia. So, as I say, to represent the biogeochemistry, Century, a somewhat simplified version of Century is included. Given my history with Savannah, so many years of its use, there are some elements that primarily the language of Savannah has been incorporated in terms of facets, for example, which is Dr. Kogenauer's term for the main vegetation groups, herbs, shrubs, and trees. And then I added a new section, which is representing the change in the percent cover of different plant groups. And so it's a kind of individual packing algorithm, kind of an agent-based perspective that I'll speak more about. So again, we have 3 vegetation facets. That includes herbs, shrubs, and trees. There is more detail than this would suggest. And so, for example, 6 vegetation layers are tracked. That includes herbs, herbs under shrubs, herbs under trees, shrubs, shrubs under trees, and then trees. And so those are tracked for every cell in the landscape. Variation in the vegetation. So for example, in the herbs, we've got annuals and perennials represented. There are the facultative deciduous, the drought deciduous plants that are included. In shrubs and trees, it's representing the deciduous and evergreen components, for example. I spoke of the individual packing algorithm. So I think in a sense of the biogeochemical pathway, the Century component of the model, as representing a square meter within each cell, no matter what the size of the cell might be. And the same is true for the individual packing algorithm. The populations of plants for each cell are known, and they are represented within 1 square kilometer. No matter whether the cell is very, very small or very large, it's represented in this theoretical 1 square kilometer. The model knows the dimensions of plants, and so it can pack individuals in, figure out how many herbs, shrubs, and trees are in that 1 square kilometer, calculate a percentage of that from that, and then subtracting it from 1 yields bare ground. These percentages then and the populations can be influenced by parameters that include things affecting establishment, like the relative seed production, how much water is available, surface litter, crowding, the herbaceous roots that can crowd as well, shading from woody cover, and then things that influence death as well, like a nominal death rate, water availability. Grazing can kill plants. The annuals have to die at a regular rate, shading from other plants, for example. And so with these control of these parameters, we can emulate dynamics and have the percent shrub, say, change on a landscape over time. And so together, it all comes together. It is a global model, the G-range, so these are cut from a global representation, but you can see the representation of annual net primary production and its change for Africa. Assessments follow. That is part of the modeling process. And so, for example, Jason Searsley took the lead in comparing G-range model results to a whole suite of on-the-ground measurements. There's a database that stores estimates of net primary production, for example, and so he could compare those to G-range estimates. And in general, it agreed favorably. In my own work, I compared the G-range global model to a suite of 11 surfaces that were either from remotely sensed data or from well-regarded simulated results. And ultimately produce images like this, which include above-ground live biomass, net primary productivity for the globe, for rangelands, and a whole suite of outputs as well can be produced. In this case, the Boone et al. Version included 1/2 degree pixels for resolution. Inputs into G-range include 22 surfaces. These are incorporating soil information, rangeland identifiers, the landscape being divided into landscape units, as we call them, the areas that are judged to be sufficiently homogeneous to be represented by one parameter set. And then in addition, there are the climate data that are used to actually drive the model. So for example, it might be CREW, if you're familiar with that database, the precipitation, minimum and maximum temperature, or it could be output from any one of the many global circulation models that drive G-range. 4 main parameter files. Again, in another video, I'll go into quite detailed explanation of those parameters, and so those will be easily understood. Outputs are extensive. It is true that it's possible to output a whole variety of information. Some of the information is output as ASCII summaries. Most of it is as binary files. So compact formed includes spatial surfaces, maps, every month for net primary production and carbon and grazing results and what have you. G-range has been available on the web for years now, in the site you see there at the Natural Resource Ecology Lab under Projects G-range. And so that has been available. It's been downloaded dozens and dozens of times. The L-range model is available as well. I'll talk more about that in another video. The G-range code is available through GitHub, again at the address that you see there. And that will remain true, but as well, I'm repeating those sources and adding to them on the lrange.org website. And so this is where the model will live long term and be available for download, all the help videos and frequently asked questions and list of publications using these tools and what have you. These resources will slowly accumulate. So in this figure, for example, this is just a screen capture of the web page. You can see the G-range model talking about what I'm introducing today. The L-range model is a localized version, and there are other versions that have been edited to connect to agent-based models and such. And then the AF-range model, which is specific to Africa and is meant to be a platform for analyses.